Welcome to lecture 12. So, we will continue what we did last time with an emphasis on declarations. So, I will quickly go through the transition system as we defined last time, and then we will continue with declarations. Right. So, we were looking at simple ML type declarations. I am sorry, ML like declarations, because type means a different word altogether. So, we have variables now, and for the present we will just assume variables have only values and they are not functions, and we have the usual binary operators and a let construct. This is the binding occurrence of the let construct. A binding occurrence in some books is also called a defining occurrence. This is an applied occurrence. Declarations are also called definitions, but we'll call them declarations. This is the grammar with non-terminals. I will use corresponding lowercase letters to distinguish the fact that I am actually interested in syntax trees and not in the grammar per se, which has other implications besides that for semantics. So, we define the notion of a free identifier in an expression, and in particular in a let construct the identifier that is declared is not free. And we define bound identifiers in this fashion, and the set of all identifiers is just the set of all free and the set of all bound identifiers. Right. We define the notion of closed terms of a language and ground terms of a language, and a complete program is closed. An expression without variables, a term without variables is ground. Then finally, we define the notion of an environment as a function. An environment over a set V of variables is just a function which maps the variables onto a particular domain of values, and an environment is a set of variable value bindings, and this function actually defines the binding. Right. So, we could go a little further and consider the set of all possible environments. I will define just environment. The set of all possible environments is the set of all possible environments over the set of all possible variables. Yeah. So, I am using this sigma notation rather than a big union. Yeah. What I mean is, if I consider unions rather than environments, rather than what is known as a disjoint summation, then there is a possibility that at some point you might have two environments which are supposed to be distinct in some logical way, but it so happens that they represent the same function. Okay. A disjoint union of sets is a disjoint union of two sets. Supposing you have two sets A and B, then a disjoint union of the two sets A and B is equivalent to having an identity associated with each element in the two sets. So, for example, if the two sets were not disjoint, if they had some common elements, then an A union B will just consist of all the elements of A and B without actually specifying an identity as to where that element came from. Okay. So, supposing you were to take some standard representations, if I take the union of the set of all natural numbers and the set of all roll numbers of BTech students, okay, that is just going to be the set of all natural numbers, because all your roll numbers are natural numbers. But if I take a disjoint union of the set of all natural numbers and the set of all roll numbers, then there is a distinct identity associated with each element. So, a roll number like 94141 will occur twice in that set, but once as a natural number and once as a roll number. Yeah. So, a disjoint union, if you want to look at disjoint unions, the best way to think of them is as having tagged the identities of the elements individually. So, if you have these two sets, then I can look upon the disjoint union as A cross, let us say, a tag. So, I will give a tag like, maybe I will just use a tag of 0 for the elements of A and a tag of, let us say, 1 for the elements of B. Okay. If I take this, so similarly, if I take the set of all naturals disjoint union, the set of all roll numbers of BTech students, then by this I am actually tagging them appropriately. I mean, so I would actually have a 94141 comma 0 as one element and 94141 comma 1 as another element, and they will be distinct, and the tag of 0 or 1 specifies which parent set it actually came from. And disjoint unions are not unknown to you, even though you may not have studied them in mathematics. You actually encounter them in programming. The variant record construct in Pascal, for example, specifies a disjoint union. There is a case which is a tag, and according to that tag you get some values. So you could have so it's a disjoint union. A variant record in a Pascal like language actually specifies a disjoint union of two sets, where the tag, the variant part of the record actually disambiguates whether an element is from one or another. Okay, I mean, I hope everybody is familiar with the variant construct. So the variant construct, for example, works as follows. You have something like a case. This is within a record declaration. Okay, something, you have some record R, let's say, type R equals record something case tag. You have to specify something which is, let's say, 0 or 1 or some such thing. You have to specify a tag of and do a case analysis of the tags. So in this case, if you have I'm using if you have 0 and 1, then you will have a case 0 of some declarations. So for example, that it might be another record declaration here, case 1 of it might be some other. Okay, but the point is that I could have case 0 of, I could have a single variable A which is integer, and in this case I could have a single variable B which is also of type integer. End case, right. So if you look at this kind of a declaration in Pascal, it really specifies that I am using integers, but I am using integers to mean two different things, and what I mean by those two different things are specified by the tag. Okay. So, disjoint unions of data types is a standard construction, though not used very much in mathematics. It is definitely used in programming, right. So, this environment, just in order not to confuse matters, this environment is a disjoint union and not a mere union, right. So, it is a disjoint union of all possible environments that you can have. So, this is the set of all possible environments as a separate grammatical entity because it has a separate logical meaning. We looked at some simple examples of sequential declarations, nested declarations, and we defined we defined the notion of updation of an environment. Here is where the disjoint union becomes effective. Okay, you have two distinct environments belonging to on variable sets which are not necessarily disjoint, and then you want to give a preference as for any identifier what value it should take in the updated environment, right. So, the updated the binding in this updated environment of any identifier I is rho 2 of I if I belongs to V2. I could belong to V1 too, but that does not matter, and if I does not belong to V2, then it is whatever is defined by rho 1. Yeah. Okay. So, we looked at the operational semantics of expressions with the usual notion of configurations, except that every now and then you have to now decorate it with a set of variables that you are actually interested in, and we had these three rules where of course now the meaning of an expression is not clear unless you can assign a value to an identifier, and that assignment of a value to an identifier is performed by the environment, and so you have these three rules now with an extra assumption. You can assume that this acts as an extra assumption. Under the assumption of an environment rho, the meaning of I is whatever is the binding defined by rho on I, and similarly the meanings of all these expressions depends on the assumption of this environment. Yeah. So, then we looked at the semantics of the let construct. So, given any let expression, let D in E goes to let D prime in E, provided D goes to D prime, and D is a declaration. So, there is a separate transition system for declarations, that is why there is a subscript of D here, whereas this entire let construct is an expression, it defines an expression. So, this transition is in the expression transition system. So, that is why the subscript E is given there. Yeah. And so which means that you are essentially, in order to evaluate a let construct, you are depending upon first evaluating the declarations that the let construct contains, and those declarations could be complex. So, you require this rule, and remember that all our transition systems are symbol manipulations. So, this declaration might during the process of evaluation get transformed into some other declaration D prime, and eventually after several applications of this, presumably you would have identified an environment, a rho prime. So, declarations give you environments, and you would probably get an environment rho prime. And now this expression is strictly speaking not in the syntax of the language. It is an expression in this which we are using in order to specify meanings in a systematic fashion. We have to specify one step transitions. So there is an intermediate state in which the environment has been created, but it is still within. So this is some sort of an intermediate specification rather than either part of the rather than being part of the syntax. Yeah. So in this environment, the meaning of this expression E, this expression E can transit to this expression with an E prime, provided in this updated environment you can show that E goes to E prime. Yeah. And so several applications of this, along with the rules for ordinary expressions and so on and so forth, should finally yield a constant, and then the meaning of this expression is just that constant. Yeah. So however, it is necessary to know that all these are intermediate steps, and eventually you are still interested in the original environment rho. You are looking at the evaluation of an expression which contains a declaration in the original environment rho, and in the process of evaluating you create a temporary change in environment in order to enable the evaluation of this expression, and once the expression has been evaluated you revert back to the original environment. The original environment is all that you have. Yeah. So these temporary changes are what I once mentioned as being reversible changes, and you can see that they will once you look at the data structures in the pragmatics, you will see that they really cannot, they really involve no work at all. Yeah. So an interpretation of the let construct according to our rules can just be defined as can be loosely specified in the following way, right. So what it means is that you first, given an environment rho, you first elaborate the definition D or the declaration D in rho, and the elaboration of a declaration yields an environment rho prime. So you temporarily change rho to rho updated with rho prime and evaluate E in this new environment till it yields an M, and then you revert back to the original environment. So several applications of the expression transition system should essentially boil down to these steps. Yeah. So that's how, but notice that this is really not, I mean I have specified it as a sort of an algorithm, but nowhere in our rules have we actually ever decided on a data structure or an algorithm. We are just saying you apply the rules, very much like we did in the towers of Hanoi problem, whether in the specification of the towers of Hanoi problem or in the execution of the towers of Hanoi problem. Just said you just apply rules which are not really algorithms, but they actually hide algorithms inside them, and some of the assumptions actually hide data structures which are fairly natural inside them, and the whole set of rules is precise, it is unambiguous, and it is by induction on the structure of the syntax, right. So let us now actually look at the semantics of declarations. As I said, this obviously, this rule E4 has obviously involves some rules that we still do not know, right. You cannot conclude this unless you can do something about this declaration transitions. So that means we have to define a new set of configurations for declarations and define a new set of rules to process declarations also in a syntax directed fashion. Yeah. So now before I get on to the semantics of declarations, let's So there is something here which I glossed over last time and again today, and that is that in this expression language I have added a row here as part of, you can think of this grammar if you like as being extended by another production which from a declaration gives you this row, okay, right. So this extended grammar, as I said, this row is strictly not part of the language, it is part of our semantical specification language, it is not part of the original language, and we use this production actually in. So if you add this production to the language, then you have various possibilities, like for example the moment you add this row to this language, you have possibilities like let row in E. You have other possibilities for declarations. You can have declarations of the form row semicolon D. You can have also things like D semicolon row semicolon D. You have all these extra constructions possible when you add this row as a new production, yeah. So now we require this extra row here as part of our semantical specification and not really as part of the language, yeah. So that is what we have used in also some of the rules which had to deal with expressions, right. So for example that is what we have used here, right. We have used this construction that you can have an environment itself as being part of the declaration, but it is not part of the language, it is not part of the original language, it is just part of our specification language if you like, it is part of this notation that we are using in order to specify the meanings of constructs, yeah. So the set of configurations that we are interested in for declarations is given by this set D, okay, where the D of course is not just of the language constructs but also includes that extra production D goes to row, yeah. So you can look upon that row as we had the base case of this declaration as I equals E and then sequencing of declarations. Now you can assume that for our specification purposes our base cases include not just this but also this, and you can therefore mix actual syntactic declarations with environments according to this grammar in any which way you like, right. So you have a collection of configurations which goes beyond just the syntactic declarations. So this D here should be understood as specifying whatever is specified, all the possible declarations that are specified by the extended grammar with this production row, yeah. And the set of terminal configurations is just the set of environments. Note there are terminal configurations, the set TD has to be a subset of gamma D, right. So that's also a good reason why you should include this row as part of this semantic specification language. Yeah, and if you did not include this row, then this important condition will not be satisfied. Yeah, right. So now that's so. As far as just our semantical specification is concerned, we will allow all this, and this is a way of, well, a patchwork way of making our language of meanings more expressive. In general, the language of meanings has to be more expressive than the syntactical language. That's how you get specification languages, okay, whose particular cases might be implementations in an existing language. I think I already mentioned once that in general specification languages might contain constructs which are probably not even implementable. Okay, so in that sense, in order to specify meanings, you require a language that is more expressive, but it's not really a formal language. It's just a language loosely specified in mathematics, and it was very convenient. Instead of, I could have specified this gamma d such that it satisfies this condition by including a whole lot of conditions which exactly specify the set of syntactic declarations and the mixtures of syntactic declarations and environments that are allowable in gamma d. But this seems a very simple and easy solution to the problem of how you can mix semantical things with syntactical things in order to specify your semantics. Yeah, so this configuration, a set of configurations, includes all those mixtures of actually the abstract environment row, because they signify intermediate steps in your computation, which since the one way of specifying the intermediate steps of your computation is to actually write out the data structures completely, write out the algorithms completely, and so on, but then that becomes too dependent on a particular implementation. You would like to abstract away from, if you are giving a language definition, you would like to abstract away from particular implementations and make it as general as possible, and this is a very simple and neat way of making your specification more expressive, so that you can specify lower level details without compromising on the abstraction from implementations, from particular implementations. Yeah. So right, so now let us look at declarations. So the base case of the declarations is when, again, the small I indicates that, the small I and the small m indicate that we are looking at trees. I agree that I is just a single node tree, but it is still a tree and not a non-terminal in the sense of the syntax of the language. So this is a syntactical construct which represents a tree, and the effect of this is to just give you a value binding. So you can evaluate this, you do not really require this environment row, of course, in order to create this new environment, but that is beside the point, because you will require this row anyway as you apply these rules. Yeah. So the next thing is, what if this construct is an expression, is a full bodied expression in itself, right? So if it is a full bodied expression, then what it means is that you have to evaluate this expression in this environment row. Okay. Now we already know the evaluation of expressions in this environment, and which means that this rule D1 will be applied several times till this expression E reduces to some constant, in which at which time you can apply the rule D0 to create this new environment. Yeah. So this is something like the induction step, which again depends upon the transition system for expressions, right. So as I've shown you these dependencies here, right. So the fact that there is an E means that you get these dependencies circularly, right. But of course it is not a circular definition. because if you do the induction on the number on the syntax is finite. So the induction on the syntax shows that you have a decreasing sequence of a descending chain of complexity of expressions. So it's the induction is perfect, it's just that it looks circular, right. Okay, then supposing you have complex declarations of this form d1 semicolon d2, then this will move to some d1 prime semicolon d2, provided in this environment rho d1 can move to d1 prime. Okay, so given a huge so which means that this movement of this declaration from d1 to d1 prime is closely linked to the application of the rule d1, where the expression only the expression moves. So if you assume that d1 is just a single declaration of the form x equals some expression, then the movement of this d1 to d1 prime is linked to the movement of this e to e prime. Yeah. And again, as we did in the case of expressions, we are looking at left to right sequential evaluations. Okay. This means in particular that even though in the domain of configurations, we have allowed configurations of this form, of such forms even though such configurations have been allowed in the set gamma d, if you strictly follow a left to right evaluation of declarations, you will not obtain these kinds of configurations ever, right. But that is okay, because in any mathematical specification you might always have redundant things, lots of redundant things, but that is okay. So what it means is that according to our rules, such configurations will never move anywhere. Yeah. So let us look at where, of course, I mean that this D is a purely syntactical entity and this D is also a purely syntactical entity. Right. So such configurations will never have any transitions. So they will be what are known as stuck configurations. Okay. So and then lastly we have to know what is the effect of sequencing on declarations, and that the effect of sequencing on declarations is just provided by this, right. So supposing you have already evaluated the left declaration in a declaration of the form d1 semicolon d2, you have already evaluated the left declaration d1 and produced an environment rho 1, and then the evaluation of d2 is sequenced in such a fashion that d2 cannot move to a d2 prime unless in this modified environment with the new set of variables d2 can move to d2 prime, right. So in order to evaluate sequences of declarations, you have to first have provided a new environment. Okay. In a more complex setting where you are not strictly constrained by left to right evaluations, where you might allow non-deterministic transitions, you could add extra rules such that such configurations also become meaningful. Okay, right. But note that in general the sequential declaration is such that, and this is something that is there in all programming languages, supposing you have a sequence of constant declarations, the second constant declaration could depend on the declaration on the first constant declaration, right. But if so, you could for example give a complex set of rules which specify that given 3 declarations of the form d1 semicolon d2 semicolon d3, if you are perfectly clear that there are no free variables in d2 which occur in d1, there is absolutely no reason why you should not evaluate d1 and d2 independently. There is absolutely no reason then why you should not evaluate d2 first and produce this environment row and then start evaluating d1 and d3. Okay. But as I said, we will be we will make it clear that our rules are such that you can have a, let us say something like a uniprocessor implementation, right. So what is the interpretation of d1 semicolon d2? It is just that you have a given environment row and then you elaborate d1 in row to yield a new environment row 1, then you elaborate d2 in row updated with row 1 yielding row 2, and then the result of elaborating d1 semicolon d2 in row is just row 1 updated with row 2. Yeah. So this interpretation, for example, does not preclude certain possibilities which are not allowed in most languages. Okay, but for example, they are allowed in ML. Take an ML like program of this form. You could, for example, have let x equals 3 semicolon x equals x plus 1 in, let us say, x star x. Yeah, this is something that is not allowed, for example, in a Pascal constant declaration. I mean, you cannot have the same identifier occurring in the same sequence of constant declarations twice on the left hand side. But here what we have here really the way we have defined this declarations is that it really allows you to first declare something like this and use that. So this x here is going to be, so the updated environment will have x equals 3 after you have processed this declaration, and that x equals 3 will be used in this to give you a new updation of x, which is x equals 4, and in that updated environment x star x will be evaluated, and so you are going to get 16. Right. So you can try this out, for example, in your ML environment, and it should perfectly allow such things. Right. So let us just go through a small example. So here is an example of a nested let construct. Right. So you have a let x equals 3 in let y equals x plus 2 semicolon x equals y plus 1 in x plus y, and you have these various syntactical elements in it, right, which I have named E0, E1, E2, E3, E4. Right. So now this is a complete ML program in itself if I want, and what I would like to do is evaluate it in an empty environment. Yeah. So the program is not hard to analyze really, but what you require to do are a few examples to make sure that your rules are right and that you do not get any configuration that is stuck, right. So let us just go through this. So and these rules also give you a reasoning mechanism which is very simple, which you can do in a top down fashion or a bottom up fashion if you like. So there's nothing in the rules which prevents you from doing it either top down or bottom up, but since we have followed a constant policy of doing things as far as possible top down, we will continue to do it top down. So essentially the question you are asking is, what does E4 go to in the empty environment phi with no predefined set of variables. So this is the empty set of variables phi. So what does E4 go to? E4 is an expression, so it has its transitions in the expression transition system, and this E4 really is so this question is the same as asking what does this do. I have skipped a few steps in between, but those are easy to fill in, right. So which is the same as saying, supposing you have processed this declaration, then what does this transition go to? So if you have the answer to any of these transitions, you have the answer to the final, right. So you can think of it either as a top down questioning, which top down recursively questioning, or if you know the final answer, you can think of it as a theorem that you have to prove with this as a lemma or with this as an intermediate step. So supposing you have the value here, you know the value here, then it's like a theorem that you can prove. I can prove that this goes to this value 11, provided I can prove that this goes to the value 11 by an application of some of these rules. Similarly, I can prove that this goes to the value 11. So I can prove that this goes to the value 11 provided I can prove this, that this goes to the value 11, and so on. So the transition of this depends upon evaluating things in the updated environment and finding out what E3 goes to. And so this phi updated with x equals 3 is just the environment x equals 3. So you are asking, in the environment x equals 3 with x as a single variable in the environment, what does this transition, what does this expression yield? Okay, and this process is tedious because it's just pure symbol manipulation. If you are actually strictly applying the rules that we have given, it's a very tedious process. But the whole point is that it hides an algorithm, it hides an execution of an algorithm in it somewhere, and is really meant to be done by a machine. Okay, so I'll cut a long story short by making some outright claims which are obvious, right. So here is a claim, right. So here are two claims. I claim that which are really obvious and can be proved using the rules, that in the environment x equals 3, y equals x plus 2 yields the environment y equals 5, and this I have put a star here to indicate that this claim might be proved in 0 or more steps of proof of the original transition systems consisting for expressions and declarations. Yeah, it may or may not, you may or may not be able to prove this in a single step of proof, but in some finite number of steps you can prove this. And what I mean is by purely mechanical process of application of the rules. And there is a further fact which I will highlight later, and the next claim is that if you have x equals 3 updated with y equals 5, which is of course equal to the environment consisting of x equals 3 and y equals 5, with the variables x and y, then this of course yields the environment x equals 6, and this again can be proved in a purely mechanical fashion. And finally we might conclude that the main body of the expression yields this so it has to be, the main body of the expression really has to be evaluated in this environment x equals 6, y equals 5, which is of course obtained by the fact that x has been redefined. So you are considering an environment x equals 3, y equals 5 updated with x equals 6, and the result of that updation is just x equals 6, y equals 5, and this yields whatever. So the whole problem boils down to just evaluating x plus y in this environment, and that finally yields 11. So I have just listed out the last 3 steps from the expressions from the expression transition system. In all these cases assume that this environment is duplicated in all these steps here before the turnstile. Right. So the final conclusion is, so if you just work back this 11 and fill up all those question marks that were given earlier with this 11, then what you have is a proof, a top down proof. What is a top down proof? I have a theorem statement and I prove that statement by saying that this theorem is proved if I can prove this statement is proved if I can prove this statement is proved if I can prove this, and so on and so forth down to the last line. Okay. So you can prove a theorem also as a set of goals to be achieved, as a sequence of goals to be achieved till you finally achieve the goal, or you can first make a guess about what is achieved, what you claim is to be achieved, and actually prove it in a normal manner. But these alternate forms of proofs are something that we have used in mathematics always. I mean, many trigonometric proofs you start with, we have to prove this, and so therefore that we can prove this provided you have proved this, and so on and so forth. So you start with the left hand side, you start with the right hand side and make them meet. But it's not a good presentation of proof, but we know that that proof can always be converted into a rigorous proof once you know the final answer. Right. So it's really in that spirit that you can look upon these rules as giving you rules for proof, and more important than just being rules for proof, after all, given a certain set of assumptions, there are probably lots of theorems that you can prove, right. So the important point here is that these rules are purely deterministic. In fact, if you look at any individual step, you know exactly which rule you have to apply in order to, well, depending on whether you are going about it in a top down fashion of proof or a bottom up fashion of proof, you know what rule you have to apply. It is purely deterministic, and in that sense it is very different from a mathematical proof. If it is deterministic, what it means is that if you can somehow encode these rules as algorithmic productions, then you have a deterministic algorithm which will give you deterministic answers, which will give you unique answers. So the form of these rules is like a mathematical theory. The forms of proofs that you want to do as a human being are also like that, but at any point in that proof there is only one rule available, and it is deterministic, and it is predetermined what rule you should apply in order to obtain the next goal from the previous goal. In that sense, it is not just a proof to be done by human beings, it has at least the potential for being implemented in a very deterministic manner. And what actually enables this determinism here is the fact that our transition systems are deterministic. The rules allow only left to right evaluation of expressions, only left to right evaluation of sequential declarations, and that itself makes them deterministic. That makes the proof process also deterministic. So for any, so given a proof there is a, so given a conclusion there is actually a unique proof, which is not necessarily true of a mathematical theory, right. So since, and this uniqueness is guaranteed by these two things. One is the deterministic nature of our rules, and the second is that this, you are always doing only induction on the syntax, or in the case of the rules we are doing induction on the extended syntax where we included row also in the syntax. So you are doing only induction on the syntax, and there is an absolutely deterministic, there is only one way of obtaining a proof if your rules are deterministic, and that means that you can actually evaluate it by an algorithm. What makes theorem proving a difficult task is that given a set of assumptions you do not know what theorem it might prove. Your theorem prover, a mechanical theorem prover, you do not know what it can prove. So the theorem prover has to be guided at all points of non-determinism in order to give you a deterministic answer, in order to work towards the goal that you are interested in. So most theorem provers are interactive, because there are two kinds of non-determinism. If you do not give it a goal, it might prove something, but that may not be what you want. If you gave it a goal, it might get confused, it might have, there might be too many different possibilities, too many different ways of proving it, and so it requires the user to guide it along some path, right. Whereas in this case our rules are such that they are purely deterministic. There is only a single way of reasoning on the induction, by induction on the syntax trees, and therefore it has a potential of having a deterministic algorithm, right. And so what it means is that the rules themselves give you essentially an interpreter design, the design of an interpreter where you want reversible changes in environments. So a nice data structure which allows for reversible changes in environments is a stack, but that is an implementation matter, that is not preached by the semantics, yeah. And the fact that it is all done by induction on the syntax tree means that you can implement the control algorithm, either the interpretation or the code generation followed by interpretation, both in a recursive descent manner as part of your parser for the language, except that the parser of the language has a more refined grammar which takes into account various things. Those things you will have to patch up, but except for that you have the glimmerings of an algorithm to implement, right. So there is the recursive descent here has to be, note that our semantics is only defined on syntax trees and not on the actual syntax that the parser uses, which is a much more refined and sophisticated form of sophisticated grammar than what we are considering in our semantics. So what it means is that the main glitch in going from here to the algorithm is to determine exactly in which point of that parsing routine you will have to include the code generation. You might have to distribute the code generation in across various routines in your recursive descent parsing. Okay, thank you.